Okay, thanks for everybody for coming back. So last week we talked about the Hopf invariant 1 problem and the relationship to the Adams-Novikov spectral sequence. And in particular, we talked about the calculation of the one line for the Adams-Novikov spectral sequence. And today I will introduce the Kervaire invariant 1 version of that story, and in particular talk about the two line of the Adams-Novikov spectral sequence. So let me begin by reminding everybody of the key fact that that we use to translate the Kervaire invariant 1 problem into a problem in the Adams spectral sequence. So I stated this last week, but I'll say it again, which is Browder's theorem, which says that the Kervaire invariant, which was this homomorphism phi k, is non-trivial in degree 4k plus 2 if and only if 4k plus 2 is of the form a power of 2 minus 2 and hn squared survives the Adams spectral sequence. Okay, we're going to switch Chuck. Okay, so first of all, hn we discussed last week. That was basically the main topic of last week, was the fate of the hns in the Adams spectral sequence. And so the Kervaire problem is about their squares. And well, one thing that's nice to notice right away is that you can trade survives for just is a permanent cycle in the Adams spectral sequence. And again, that's just because, well, a permanent cycle survives if it's not a boundary. And this thing is in filtration 2. So it would only be a boundary if it was hit by a D2. And there are no classes in the zero line in that degree that could support such a differential. So it's just a question of whether it's a permanent cycle. Okay, and yeah, let me make a remark to remind everybody about these terms. So first of all, hn was this class C1 2 to the n in X1 of the dual Steenrod algebra. So as I explained last week, that turns out to be, just via the Kobar complex, the subspace of A star consisting of coalgebra primitives. And since you're in characteristic 2 and C1 is a coalgebra primitive, so are its powers of 2 on it. And those are all the primitives. And well, we showed that H0, H1, H2, H3 are permanent cycles corresponding to the real numbers complex, the H and O, RC, H and O. And this implies that their squares are permanent because it's a multiplicative spectral sequence. So the way we defined it, it was a ring object in filtered spectra. And so you can think of this as saying, well, if I have lifts to the homotopy groups of the filtered spectrum of each of these classes, then their squares are lifts of the squares of the classes on associated graded, because the projection map to the associated graded is a ring map. Okay, so so that's what happens sort of in low dimensions, and then we had this differential of atoms when n is greater than or equal to 4, which in particular implies that when n is greater than or equal to 4, that the hn squared class is a D2 cycle. That's just because the Adams spectral sequence is a spectral sequence of F2 vector spaces, and so when I apply the Leibniz rule to this, I get that these are D2 cycles. So I remarked last week that in some sense, D2 differentials in the atom spectral sequence are relatively algebraic, and they're determined by these secondary Steenrod operations. But we can already see that, well, in order to say something about the fate of the squares of these classes, we have to move on to at least D3s to say something. So this becomes already a more difficult problem.
I'm a bit confused. I think this is just saying that the target is always two torsions, so any square will have 0 D2, right?
Yeah, so any square will be a D2 cycle, yeah. Yeah, so it doesn't depend on this differential. Any square will be, but yeah. Exactly, so this is a square on the E2 page, so it's a D2 cycle, but it's no longer a square on the E3 page because of these differentials. So maybe that's a better way to say what I wanted to say. Okay, and also let me just tell you what the 2 line is in the atom spectral sequence. So this consists of, first of all, the squares of the HNs, and the products HN times HM, where M is not equal to n plus 1. So in other words, the 2 line is spanned by all the products of HI and HJ, subject to the relation that HI plus 1 is 0. Okay. Okay, so that's the 2 line in the atom spectral sequence, and it's where these HN squared classes live that somehow control this Kervaire invariant. Okay, so now let me say what's happening in the 2 line of the Adams-Nabokov spectral sequence. Okay, so last week we computed the 1 line via the chromatic spectral sequence, although I don't think I actually said that word, but the chromatic spectral sequence is really just using these short exact sequences of BP star BP comodules where I sort of invert one height parameter at a time and then look at all of the torsion for that height parameter. And if I took all of the long exact sequences associated to those short exact sequences and splice them together, I would get an exact couple, which gives you the chromatic spectral sequence. So there's sort of a more robust version of the way that I presented this height 1 calculation. But the upshot is still the same, which is that somehow calculating the E2 page can be reduced to doing calculations of this continuous group cohomology for the Morava stabilizer group. And so I won't say anything more about how this theorem is proved, other than that it is through that approach. And then let's just take what they prove and use it. So I won't say what the whole 2 line is, like I did here, but just in the degrees we care about. So in the degree of the Kervaire element. So they do some hard calculations with the Morava stabilizer group to conclude that first of all that this group here is always simple 2 torsion. And so by the same kind of long exact sequence argument that we saw last week, this is going to be isomorphic to the X1 group for BP star mod 2 via the boundary map for the multiplication by 2 long exact sequence, which I'll just call delta 2, or partial 2, I guess. And, well, it has the following basis. This should be an N. Okay, so I'm introducing another boundary map that I'll define in a second. Okay, so let me first say what this, I guess I'm using partial 1 is. So this is just an analog of what we saw last week. I have the following short exact sequence of BP star BP comodules, and this partial 1 is the boundary map on X in that. Okay, and I wrote some S's and K's here and didn't define them, but they are the ones so that they're in the right degree. Okay, so for the positive values of S and K that make that in the right degree, those are on this list of basis vectors. And I'm going to just state a couple more facts about this basis. So first of all, I want to give a name, 2 to the n minus 1. So I'm going to define this class beta 2 to the n minus 1 over 2 to the n minus 1 to be partial 2, partial 1 of this class here. So this is the basis vector here I get when S is equal to 1. This is this class beta 2 to the n minus 1 over 2 to the n minus 1. And we need to know something about it. So turns out that this has a very nice cobar complex representative mod I. So I is the same ideal as last time, the one consisting of all of the VIs. So this is sort of defined as this double boundary class, but it turns out to be this class in X2. Okay. Let me just say a couple more things and then kind of unwrap this theorem a bit.
Can you say again with I?
Yeah. Just this ideal consisting of all the VIs.
And what is Ti?
That's T1. It is the, I'll just write this here. So I'll need it in a moment. So BP star is this polynomial on the VIs. And BP star BP is polynomial over BP star on classes Ti. So their classes appearing in the Hopf algebroid BP star BP. Okay, I'll say more about them in a second. What I want to say for now is just the following observation, is that every basis vector here except this one, so all basis vectors are in the ideal 2, V1, V2. Okay, so well, that's actually kind of obvious because I'm saying that, well, first of all, these two are obviously in that ideal because they're divisible by V1. And this one is for this sort of similar argument that I used last week, where I can sort of introduce a filtration on where these things live. That's sort of the adic filtration with respect to this ideal. And I can do that also after inverting one of the parameters where I say, the filtration of this fraction is the filtration of the top minus the filtration of the bottom. And except for when S is equal to 1, that will make this have positive filtration with respect to this ideal, and the boundary maps will sort of respect that filtration. So I will know that since this class was in positive filtration with respect to this ideal, so will its boundary be. Okay, so except for this case, all of the basis vectors are sort of this height less than or equal to 2 ideal. Okay, so then I can finally tell you what the map from the Adams-Novikov to the atoms does in this degree.
Christian,
Yes.
in your definitions of these betas,
Yeah.
both 2 to the n minus 1 or 2 to the n minus 1?
There shouldn't be an m anywhere, just all n's. Sorry. Okay, so what does this map do? Well, it sends beta 2 to the n minus 1 over 2 to the n minus 1 to hn squared, and it sends all the other basis vectors to 0. Okay, so let me first explain the second claim. Well, this map here is induced by this map of Hopf algebroids, which in the left coordinate is just the quotient by I, and in the right coordinate is the one that sends the TI classes to the square of the XI Milnor generators. Okay, so on one hand, the second claim is clear because I told you that every class except this one was contained in this ideal, which is in particular in this ideal, which is killed by this map. And for the first claim, I mean, that follows just from taking this and using our description of hn squared. So hn is this class, so hn squared is this tensor itself as an element in the Kervaire complex, which is obviously what this is sent to. Okay, so let me just stop there because I said a lot and try to put this all in some context. So in the Hopf invariant 1 version of this story, we had some class hn living here, and we wanted to say, okay, if this is a permanent cycle, then it has to admit a lift to the Adams-Novikov spectral sequence that's also a permanent cycle. And then we just computed that this map was 0, so that could never happen. Okay, but here it's not 0. There is exactly sort of one basis vector that's sent to it, and so we want to try and control this element a bit and understand, how this behaves in the Adams-Novikov spectral sequence. Okay, any questions on that? That's sort of the computational input to most of the rest of the story. Yeah.
What was the argument for showing that the other divided beta classes are in this ideal?
Are in this ideal?
Yeah.
Okay, so these two are clear, right? So for this one, what I do is I say, let me introduce a filtration on all of these Kervaire complexes, which is the adic filtration for this ideal. And then I show that the maps on X groups, in particular the boundary maps, respect that filtration. In the same way that I did last week, I sort of take the I-adic filtration on this, invert the filtered V1 in filtered BP star BP comodules, and then take the co-kernel. It gives me a long exact sequence in filtered X groups. And and then the point is that these other divided beta classes are the ones where S is positive, which gives this positive filtration. So its boundary also has positive filtration.
So there was nothing transquadratic happening?
No.
It's just,
Yeah, I mean, when S is 1, then the filtration is 0, and something can happen, and that's what this beta class is there for. Okay. So, I guess a lot of work goes into just this one theorem, but let's just use it. Okay, so I guess as a bit of a word on where we're headed, we're going to now look at some simpler X groups where this beta class is still detected and try and sort of understand it there. Okay, and so for this, we're going to need to look at the Morava stabilizer group again, in particular at finite subgroups. Okay, and so to motivate a lot of what I'm going to talk about now, let me just say that the Ravenel noticed that at odd primes, well, there's an analog of this beta class. I won't define it, but let's just say it's defined analogously and behaves analogously. He noticed that this is detected by following map. So if I take this gamma formal group that we talked about last week at height p minus 1. And I take that formal group, that there's a CP in the automorphism group of this. So in particular in this GP minus 1. So that defines a map of stacks like this. And what he showed is that, that this class here is detected by this map, in the sense that when I look at the map on X groups going the other way, its image is non-zero. And that's really great because calculating group cohomology with respect to a cyclic group is really easy. I said that last week, but let me remind you why that is. It's because there's a very canonical, easy resolution of the trivial module, of the trivial CN module, and it's this one. So let me let gamma be a generator of Cn. Okay, so I have this canonical free resolution of the trivial Cn module, and this resolution is two periodic. And so in particular, if I take the cohomology of the trivial module, I'm going to get a class in H2 that sort of acts like a periodicity generator. And more or less what happens is that he shows that this class here goes to this class times an appropriate unit.
Are you going to comment why this is detected by this?
Yeah, that's more or less what this section will be about.
Oh.
So we'll give a sort of sketch proof of this. Yep. Okay, so to get there, we need to open the box a bit about this Morava stabilizer group and p-typical formal group laws. So let me just state some key facts. So if I have a morphism of p-typical formal groups, say G from F to big G, then this can be expressed uniquely in the following way. So G is a power series, and it can be expressed as the following formal summation. Okay, so first of all, these TIs that are appearing here are the same TIs up there. I mean, here they're just some elements in the ground ring, but the TIs in BP star BP are the universal ones. And this G below the summation is just the formal summation provided by the formal group law G. Okay, so that's some bivariate power series, and that's what that notation means. And the point of this description is that I'm only seeing powers of p in the exponents. Okay. That's the first thing I want to say. Next thing is that, well, if I have some map like this, classifying some automorphisms of a p-typical formal group law, then actually the map induced on Hopf algebroids can be described really explicitly. So first of all, I told you that these quotient stacks have the property that their sheaf cohomology corresponds to group cohomology. And one way of proving that is to just write down a really explicit Hopf algebroid presentation of this stack, and it's this one. So the ground ring is this Laurent on R, and then these are functions from G to that. And the structure maps are sort of what you would expect. Okay. So I want to explain how this map is described explicitly. So the map in the first coordinate is, of course, the one classifying the formal group. And the map in the second coordinate is as follows. So it sends Ti to the function, which sends an element in the group G to, well, what I'll call Ti of G. So it's the thing where I express G in this way and take the term Ti. So people sometimes like to say that you should look at the TIs in BP star BP and think of them as functions on the Morava stabilizer group. And this is what that means. Okay, so the point here is just that this map of Hopf algebroids can be described really explicitly. And of course, I want to apply this to subgroups of the Morava stabilizer group. So now let me give you some facts about the Morava stabilizer group that we will need. Somehow not so much. But let me say that the kind of point of view on this that I want to explain is that the Morava stabilizer group is better understood by, instead of looking at the automorphism group of some formal group law, rather looking at the endomorphism ring of it and using some properties of that to understand this as a sub. Okay, so first of all, this is a ring because, well, basically because gamma H is an abelian group. So in particular, these endomorphisms consist of power series, but I can add them together with this rule. So that's why this is a ring. And in particular, it's a very nice ring. It's a non-commutative DVR. Okay, so it's like a DVR, but non-commutative. And in particular, it has a valuation on it, and it's the one as follows. I say the valuation of a power series f of x is greater than or equal to k if f can be divided by the Frobenius k times in this sense. Okay, and this valuation is sort of rigged up so that when I apply it to P in this ring, I get the height h. Okay, and that's like more or less the definition of height, because P is the P series here. And the uniformizer is the power series x to the P. Okay. All right. Next, I want to say, well, this is a non-commutative DVR, so if I invert the uniformizer, which is the same as inverting P in this case, then I get a division ring over QP. So this is something in the Brouwer group of QP, and the valuation extends in the usual way to this DH, and I can recover, the automorphism group gamma H as the things of valuation 0. Okay, so rather than sort of going directly at this group, it's useful to understand instead this endomorphism ring and really this localization of it. And
Question, the fx equals to g of, what is g again?
sorry, if there exists G such that f of x can be written like this. So it's like saying, I have my power series f of x, but when is it the case that all of the exponents of x that I see in that power series are divisible by p to the k? Yeah, and that's how this valuation is defined. Okay, and let me just say kind of the nice fact that goes into proving all of this, which is this really straightforward lemma that somehow buys you a lot, which is that if I have f in this endomorphism ring, and its derivative at 0 is equal to 0, then I can divide it by the Frobenius in that way. And the proof of this is just to say, well, let me think of this as a Lie group, and f is an endomorphism of the Lie group. So if its derivative is 0 at the identity, then by translation, its derivative is 0 everywhere. So its derivative is 0. And it's a power series in characteristic P, so that means that the only exponents in this power series were divisible by P. Okay, and so you can sort of iterate that to show that this thing here is well defined. Okay, let me see. Okay, yeah. So I sort of just giving a lot of background for now that we will use later, so just bear with me. So I said that this is an element in the Brouwer group. And let me just remark that this Brouwer group is known. And this isomorphism is via something called the Hasse invariant. I won't need anything about that, but let me just state some useful facts in this kind of world here that we will use. So let's suppose we have any finite extension of QP. Then the usual valuation on QP extends uniquely. So this is an extension of local fields to one on nu L, on L via the formula. Well, I take the norm of an element X in the field L, and then I have an element in QP. And then I take its valuation and then divide that by the degree of the extension. Okay, and kind of crucially, it's unique, this extension. Okay, one last kind of just fact I'm going to state is that if I have a division algebra D in this Brouwer group, and it has rank n squared, then every extension of QP of rank, of degree, let's say, dividing n, is contained in D. Okay, so give you guys a moment to digest that, but also all of these things I'm saying are sort of the minimal things we need to understand this observation of Ravenel that I said above. So that's where we're headed with this. So, by the way, these are all facts you can find in Serre's book on local fields. And thankfully, kind of the way that we use these facts, we don't have to understand them, really. So that's kind of something I'd like to emphasize. Okay. So anyway, the point is that this third fact here gives you a way to find subfields of D, and the second fact allows you to compute valuations in those subfields. And that actually allows you to find all of the finite subgroups in the Morava stabilizer group. So let me just state a theorem due to Hewitt. So what he actually does is he classifies all the finite subgroups in all the Morava stabilizer groups. But I just want to, well, pick out some subgroups that we need for the Kervaire problem. So as a very special case of what he proves, there is the following subgroup when my height is p to the n minus 1 times p minus 1. Okay, and the proof is is quite easy. Well, first I claim I can construct the following tower. So, okay, this field extension here has this degree, and so the third point over here tells me that I have this containment here. So that tells me I have an element of order p to the n in this division algebra, and I just need to check its valuation to 0, and then I have a cp to the n subgroup of here. Okay, and I can compute its valuation using that formula. So if I want to compute the valuation of d, of this primitive root, well, first I take the norm of it, and then I take the valuation in QP and divide by the height. We'll just call it h for now. But the point is, I mean, what is taking the norm is like multiplying this by all of its Galois conjugates, which is just multiplying all the elements of a cyclic group together, which is either the identity or the unique element of order 2. And so this norm turns out to be plus or minus 1, which in either case has valuation 0 in QP. So this also has valuation 0, which tells us that it's actually in the Morava stabilizer group. Okay, so that's a very easy way to produce these cyclic subgroups by these roots of unity. And okay, but how do you actually understand anything about the power series in the Morava stabilizer group that this corresponds to? So that also comes down to these valuations. So I have some element, zeta p to the n, and it's in this p-typical endomorphism ring, so I can write it like this. Okay. And, well, I told you, maybe it's erased by now, but I told you that, like, that these beta p to the n classes have cobar representatives that are like t1 to a power tensor t1 to a power. So I would really like that this thing sees t1. So I would like that the first coordinate of this is non-zero. That's gonna turn out to be enough, that this t1 is non-zero, which is just asking, well, if I take the element in this endomorphism ring, zeta p to the n minus 1, I would like it to look like t1 x to the p dot dot dot, which is to say I would like its valuation to be 1. Okay. So the minus 1 here is the minus in this endomorphism ring, which 1 is the power series x, because it's the identity element. And so this minus 1 is why this x came over here. Okay. So I just need to check that this is true, and I won't do that. But it's just this norm thing. Okay. So now let me maybe quickly state.
You check, I think at this one point, you check that this valuation is 0.
Yeah.
So then by part C there we get an element in the automorphism group.
Yeah.
But do we know that it's a CP to the n? So I think
It has order p to the n because it's a primitive p to the nth root of unity. Everything is a sub of this d, so its order is the same. Yeah. And yeah, I mean, somehow, I don't know, if you wanted to actually write down all these coordinates, maybe it wouldn't be so clear from the way you abstractly got it from this field theory, but you can at least compute valuations as much as you want, and you can check this, and there's no problem.
Part C, I think I didn't understand, is F lying in endomorphism of gamma, or is in the DH? In part C? You say F such that valuation of
Yeah, sorry. I really should say f in end gamma h, I guess. But I think it doesn't matter. Yeah. I think it's okay either way. Okay. So let me state something as an exercise. if I look at this class in BP star BP, here is its coproduct formula, and this is just for degree reasons. So this is a coproduct formula in BP star BP. So let me say some things for a moment about this map here, from sort of induced by this map of stacks, going from X over MFG to this group cohomology. Well, I'm going to know that this T1 along this map goes to something non-zero in this Hopf algebroid. Which is this functions here. And better, it goes to something which is a coalgebra primitive, because it was in BP star BP. And and this is going to tell me actually that if I look at these classes in X2, which represent these beta classes, that these are going to go to some power of u times t, where t is this class in H2, the periodicity generator in group cohomology. Okay, so this is an exercise, I'll say. And if you don't know how to do it, you get stuck, look in Ravenel's paper on the odd primary Kervaire problem. He sort of works out why this is true. But these are the pieces. You need to know that it goes to something non-zero, and it's a coalgebra primitive. Okay, so maybe in the couple minutes before the break, I want to summarize. Well, I just gave you a ton of information, and I want to just emphasize what the upshot is for the actual Kervaire problem. So let me go back to p equals 2 for a moment. So there we somehow care a lot about these classes beta 2 to the k over 2 to the k. And we learn that this is detected by the map as follows, with the C2 to the n quotient. So we produce that subgroup over here. Okay? And, well, this is true for any n. Okay? But the junk in the Kervaire degree, besides these beta classes, is height less than or equal to 2. Okay, because I don't have it up here anymore, but I showed that the rest of the classes were contained in this ideal 2v1, v2. And so what I'd like to do is I'd like to choose this n of height greater than 2. Because then what that does for us is it makes the map induced on X from this look exactly like the map from the atoms-Novikov to the atoms. In particular, it makes it have the same kernel. We know that the beta class always goes to this periodicity generator, and we'd like it to have the same kernel as the map to the atom spectral sequence so that we can really translate the whole problem into this picture somehow. Okay, so that's why we want to take actually n to be such that this height here is greater than 2, and the smallest n for which that happens is 3. So that tells us that the sort of minimal case to do what we want is to look at height 4 with the C8 action. Okay, and those are like the parameters appearing in the HHR paper. They do a height 4 theory with a C8 action. And that's why. It's sort of, I can get the class that looks like hn squared in the atoms-Novikov to be detected here for any n, but it's detected in a really nice way if I go take my height greater than 2 because it throws out all the other junk. Okay, let's take a break now.